Imagine watching a shattered glass leap off the floor, reassemble in midair, and land intact on the table. You'd call it impossible, not because any single atom can't move that way, but because the odds are absurd and the arrow of time seems nailed down. Now take that intuition and aim it at the darkest objects in the universe. Black holes swallow matter and information, and to our everyday sense of physics, they only go one way. But Einstein's equations contain a strange mirror image. A white hole, an object you can't enter, only exit. Here's the open loop. If a white hole is the time reversal of a black hole, does it literally reverse entropy? Could it spit out a future that looks like our past? And if physics even allows that on paper, why don't we see white holes lighting up the sky like cosmic fountains right now? To understand why this question is so slippery, start with what we mean by time's direction. The microscopic laws we use in physics, Newton's, Maxwell's, even quantum mechanics in its basic form, mostly don't care whether time runs forward or backward. Reverse all velocities and, in principle, the equations still work. Yet our lives are built on processes that clearly prefer one direction. Eggs scramble, never unscramble. Heat flows from hot to cold. Memories accumulate of the past, not the future. The usual explanation is statistical. There are vastly more disordered states than ordered ones. Entropy is basically a measure of how many microscopic arrangements correspond to the same macroscopic appearance. A tidy deck of cards is one arrangement. A shuffled deck is many. Randomly shake the system, and you almost inevitably land in one of the many disordered options. Gravity complicates this comforting story. If you take a gas and let it expand, entropy rises. But if you take matter in space and let gravity pull it together, it clumps. Stars form, galaxies form. It looks like order, but it's not. Gravitational clumping actually increases entropy because the system gains new ways to rearrange itself. Heat, radiation, and ultimately the extreme entropy associated with horizons. This is where black holes enter. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes aren't just simple sinkholes. They have entropy proportional to the area of their event horizon, and they have a temperature. That was shocking because entropy is supposed to count microstates, the hidden details you're not tracking. A black hole's horizon area behaving like entropy suggested the horizon is hiding an enormous number of internal possibilities. So, what about white holes? In the simplest version of a black hole, the Schwarzschild solution, there's a maximal extension of space-time, a more complete map than the one people usually imagine. In that full map, the black hole region has a time-reversed partner, a white hole region. Mathematically, if a black hole is a place where everything can fall in but nothing can escape, a white hole is a place where nothing can fall in but things can emerge. It's not anti-gravity or a portal. It's a different causal structure. And crucially, it's not something you build by reversing the spin on a cosmic drain. It's a boundary condition. You're specifying that for some reason, the space-time contains a region that is already there, already arranged so that world lines emerge from it. Now, the deep question. Does that mean entropy is running backward? Not automatically. Time reversal in the equations doesn't force time reversal in the thermodynamic sense. The laws permit a movie to run backward, but that movie requires fantastically special initial conditions. A white hole is exactly that, an exquisitely tuned condition on the geometry and the matter fields. Think of a black hole as a funnel. Lots of different messy initial situations, dust clouds, stars, gas, can collapse into something that looks, from far away, like the same black hole. That's why black holes feel natural. They're attractors. A white hole is the opposite. It's like having a funnel that spontaneously emits a perfectly coordinated spray of water droplets that just happens to look like it came from a cup you spilled yesterday. The slightest interaction with the outside world tends to spoil it. There's also a stability problem. In a white hole spacetime, the horizon is a one-way membrane in the opposite direction. Signals can escape, but cannot enter. That sounds safe, until you realize the external universe can still influence the region near the horizon. Any stray particle hovering outside can get infinitely blue-shifted when traced backward in time toward the white hole horizon in the idealized solution. In more physical terms, tiny perturbations tend to pile up and wreck the clean nothing-can-enter boundary. Analyses suggest classical white holes are violently unstable. They either turn into black holes or smear into something that no longer resembles the neat, time-reversed object. Then there's Hawking radiation, the quantum leakage that makes black holes evaporate. A black hole slowly emits thermal radiation, increasing the entropy of the universe overall. If you time-reverse that process, you don't get a white hole casually emitting matter. You get something absorbing a perfectly tuned bath of incoming radiation. Radiation correlated in precisely the right way to make the hole shrink in reverse. That's not just unlikely, it's essentially never produced by ordinary astrophysical conditions. A real entropy-reversing white hole would need the environment to conspire with it, delivering the exact negative of the scrambling that normally happens. So what physics allows is subtle. General relativity allows a white hole geometry as a mathematical solution. It allows local decreases in entropy too. Fluctuations happen. But a macroscopic, persistent object that looks like entropy running backward is a statement about global conditions. The whole surrounding universe would need to be arranged in an extraordinarily special way. In the language of thermodynamics, white holes are low-entropy past conditions masquerading as objects. Why does any of this matter? Because it exposes the seam between the laws and the initial conditions. We often talk as if the laws of physics create time's arrow, but the equations mostly don't. The arrow sneaks in through the universe's starting point, an early cosmos that, for reasons we still debate, was in an exceptionally low entropy state. Black holes then become a kind of entropy engine, converting relatively simple matter into enormous hidden complexity behind horizons, while radiating energy outward. White holes would represent the opposite, complexity emerging already coordinated, like smoke unmixing from air. This also connects to modern puzzles about information. If black holes evaporate, where does the information go? One camp says it's encoded in subtle correlations in the outgoing Hawking radiation. Another suggests dramatic effects at the horizon. Others explore quantum gravity resolutions. White holes sometimes appear in speculative models as a late-time bounce, where a black hole transitions, through quantum effects, into something that releases what fell in, like a delayed echo rather than a literal time reversal. In those ideas, entropy doesn't run backward globally. It still increases, but the geometry might allow trapped information to re-emerge after unimaginably long times. That's different from a pristine white hole. It's more like a black hole with an escape clause written by quantum gravity. So, where do we land? A white hole is not forbidden by Einstein's equations, but nature doesn't seem eager to create one. To get a true time-reversed black hole, you'd need a universe that is already arranged to produce it, with incoming conditions so fine-tuned that any realistic noise would collapse the trick. Entropy reversal isn't banned locally, it's just astronomically expensive in probability. Black holes feel inevitable because disorder makes them. White holes feel mythical because they demand pre-arranged order. And that's the mic drop. The strangest objects in relativity aren't just about gravity. They're about why the universe had a beginning that made time itself pick a direction. Subscribe if you want more physics at the edge of what reality allows.